Greetings of the day. I am Dr. K. Srishailam, Professor of Physics, Assistant Professor, Department of Basic Sciences, School of Sciences and Humanities, SR University, Warangal, Telangana. Today I am going to discuss about Newtonian mechanics, the outlines of the topic, elements of vectors, Newton's laws of motion, law of universal gravitation, work energy principle, conservation of energy, conservation of linear and angular momentum, elastic and inelastic collisions, then applications of Newton's laws and conservation laws. So now we discuss some basic concepts related to this topic. So now the physical quantities are divided into two categories. One is scalars and another one is vectors. How we can define the scalar? The scalar is nothing but it has only magnitude but no direction. That physical quantity is called scalar. So example, mass, length, distance, etc. These are all called scalars. Now coming to the vector, so the physical quantity which has both magnitude and as well as direction. As well as direction. Such physical quantities are called vectors. So example, velocity, acceleration, and so on. Next, how we can represent the vector. Representation of the vector. So the vector is represented with, for example, OA. So it starts from O. Now this point is called tail and this point is called head. So we can represent the like this, or OA with arrow mark, or we can simply represent with bar over the vector. Okay. Unit vector. Unit vector is nothing but the magnitude of the vector is 1. So that is called unit vector. It is represented with a cap. Okay. So now how we can find the a cap? A cap equals to that vector by magnitude of that vector. So this is by using this we can find the unit vector. Now coming to the position vector, next resolution of vector. Consider the case of vector A with its tail at the origin. Consider the rectangular system. Now tail is at origin and this is vector A. So we can resolve this vector into two components. So if we draw perpendiculars onto the x and y from this, so the it makes an angle theta with x-axis. The intercepts are ax and ay. So here I is the unit vector along x-axis and j is the unit vector along y-axis. So now the coordinates of A is x comma y. Now vector A we can represent like this: axi plus ayj. So here ax equals to a cos theta and ay equals to a sin theta from the figure. Okay. Now the magnitude of the vector A is magnitude. So is equal to root over x square plus ay square, or so if we consider these two, so a equals to root over a square cos square theta plus a square sin square theta, and the direction is tan theta equals to the direction of the vector tan theta equals to mod of ay by ax, or we can write theta equals to tan inverse of ay by ax. So coming to the vector addition, the vector addition can be done in two ways. So one is triangular law of vector addition. Another one is parallelogram law of vector addition. And this vector addition obeys the two laws. One is commutative law. Commutative law is nothing but that is a plus b is equals to b plus a. And associative law. The associative law a plus b plus c is equal to a plus b plus c. Now parallelogram law. So here the definition of the parallelogram law is two vectors acting simultaneously at a point are represented both in magnitude and direction by the two adjacent sides of a parallelogram. For example, these two are adjacent sides of the parallelogram. Now, two vectors are considered P and Q. So this is vector P and this is another vector P and Q. Now the angle between them is theta. Now the resultant of these two, consider it is R. R equals to P plus Q. Now this point is O and this point is A. P is a vector and Q is a vector. Now this point is B and this point is C. Consider this point is D. Now this is also angle theta same. Okay. Now this angle is alpha. Now, so the magnitude of R resultant vector is equals to root over p square plus q square plus 2pq cos theta. So now I can write here the magnitude of vector resultant vector is root over p square plus q square plus 2pq cos theta, and the direction of the resultant vector, that is tan alpha. Tan alpha equals to, from the figure, so it is clear that now this is vector q and this is also parallel to q. Now this is vector p and this is also parallel to p. This is q, sir. Now tan alpha equals to, from the figure, CD by OD. So we can write CD equals to, OD is nothing but OA plus AD. So therefore CD is nothing but Q sin theta divided by P plus, this OA is P plus Q cos theta. So this is the direction of the resultant vector. Now coming to the dot product, the scalar product or dot product of two vectors. For example, consider two vectors, vector A and vector B. So the dot product between the two vectors is defined as, or we can write, so for example, A dot B, so is equals to mod A mod B cos theta. So these two vectors are, this is vector A and this is vector B. The angle between them is theta. So now so the dot product between the A and B is, we can write like this, or cos theta equals to A dot B by mod A mod B. So here the dot product of the unit orthogonal vector. For example, you take consider x, y, and z axis, x axis, y axis, z axis. This is the origin. Unit vector I, j, and k. So here I, j, k are called orthogonal vectors of these, are unit vectors along these three axes, x, y, and z axis. So the dot product of these orthogonal vectors I dot I equals to j dot j is equals to k dot k equals to 1, and I dot j equals to j dot k equals to k dot I is equal to 0. So this is very very important. Now I dot I, j dot j, k dot k is 1, and I dot j, j dot k, k dot I or I dot k is 0. So examples, the work done. For example, consider two vectors. So this is vector A and vector B. So the angle between them is theta. Coming to the cross product, so the resultant vector is in this direction. this resultant vector is perpendicular to both the vectors and plane containing. So now this C vector C equals to A cross B. So now A cross B is equals to mod A mod B sin theta into n cap. Therefore, sin theta into n cap. This is a unit vector is equals to so A cross B by mod A mod B. So how we can determine the A cross B? A cross B is equals to, for example, consider the A vector. A vector equals to um, AXI plus AYJ in two dimensions. B vector equals to BXI plus BYJ. So A cross B is equals to IJ. If we consider three-dimensional A dot K, so here also BXI BYJ plus BZK. So IJK. So write the first I component is AX, AY, AZ. Next BX, BY, and B. By using this procedure, we can determine the A cross B. So how we can define the force? Force is nothing but which changes or tends to change or restore uniform motion of the body. So that is due to the force there is a change in the motion of the body. For example, if the object is in motion, so we apply some force on this. So now its velocity reduced. Sometimes it comes to rest also. Now unit for force newtons. There are two types of forces. One is contact force. Another one is non-contact force. So coming to the contact force, the contact forces act on the objects when they are in physical contact with each other. For example, these two objects are the object A and object B. These two are in physical contact. So then only the contact force is existing. So example, tension. Non-contacting force, the force acts on the object without direct physical contact. Without direct physical contact. So for example, this is the earth and this is the sun. So there exists a force. This force is gravitational force. So example for this gravitational force. So no physical contact between these two objects, but there exists a force. That force is gravitational force. coming to the Newton's laws of motion. So in the year 1686, Isaac Newton described the relation between force and motion. Force and motion. So in the year 1686, Newton first describes about force and motion. Now he proposed three laws. That is, Newton's first law is the statement is every body, for example, this is one body represented with A, its mass M. Every body continues to be its state of rest or uniform motion in a straight line until and unless external force is acting on that. For example, this object is moving, so it is always in motion until and unless an external force is acting on that. Now, this gives the concept of force and inertia. It gives the concept of force and inertia. Examples: the passenger in a stationary train falls backward when the train starts suddenly. The passenger in a stationary train, now the train start, so the passenger falls backward when the train moves suddenly. And the second example, a body released from artificial satellite, for example, this is Earth, it continues move in the same orbit at the same speed. So the object is released artificial satellite from an artificial flight, right? This object continues its motion around this. Now the sparks emitted from grinding stone, for example, this is the grinding stone, so the sparks like this. Coming to the Newton's second law, the acceleration of an object is directly proportional to the net force acting on the object and is inversely proportional to the mass. So the direction of the acceleration is in the direction of the net force acting on the object. So for example, this is one object. A force is acting on this. Due to the force, so it is accelerated. So its acceleration is A. This A, its mass is A. This A is directly proportional to the applied force and inversely proportional to the mass of the body. So now, so that is F equals to MA. Or we can write sigma F equals to MA. Also we can the rate of change of momentum. So we can say that is F external is equals to the rate of change of momentum. Momentum is nothing but mass multiplied with its velocity of the object. So when we apply the force, the object comes into motion. So now the product of the mass and velocity is its linear momentum dp by dt. So therefore f external equals to d by dt of p is nothing but mv. So m is constant, f external equals to dv by dt. The rate of change of velocity is acceleration, that is f external equals to ma. So if If external equals to 0, what happened? If no external force acting on the body. So no force, no acceleration. If the force is 0, that is external force is 0, now no acceleration in the body. So that is F external equals to 0. So acceleration is also 0. Newton's third law. The statement is for every action there is always an equal and opposite reaction. So for example, two objects are there. This is object A and this is object B. Or this is one object 1, this is object 2. So the force exerted by the first object is 1 onto the second object F12. The force exerted by the second object onto the first one is 2 1. So now the relation between these two is F12 is equal to minus of F21. Examples: push against the edge of a desk. Desk pushes the back against your hand. So next example, rocket motion. So the rocket motion is the best example. So next one important, this is law of universal gravitation. So the statement is, for example, you consider the two massive objects. One its mass is m1 and another mass is m2. These are separated by a distance r. Then there exists a force. That force is gravitational force. So this information first introduced by Newton. So that's why we call it as Newton's gravitational law. Now the gravitational force between the two objects is proportional to the product of the masses. That is the force between the two massive bodies proportional to the product of the two masses m1 and m2 and inversely proportional to the square of the distance between them. So by combining this f, by using that f proportional to m1 m2 by r square, we eliminate this proportionality, we get one constant, that is g m1 m2 by r square. So this g is called the universal gravitational constant. So this is universal constant value. Okay. So where m1 and m2 are the masses of the bodies. Now we see the relation between small g and capital G. Now this is the, its mass is capital M. This is the small object which is on the surface of the earth. So from center to earth surface the distance is r. So in that case there is, according to previous Newton's law, Newton's gravitational law, there exists a force. So that force is nothing but capital M proportional to product of the two masses. Now F inversely proportional to square of the distance between them. F proportional to capital M small m by r square. We eliminate this proportional F equals to G into capital M small m by r square. Now this is consider it is equation number 1. So according to Newton's second law, F equals to mg. So there is a gravitational force. So now this is equal, both LHS are equal. So that is mg is equals to g into capital M small m by r square. So gets cancelled. So we get g equals to gm by r square. Now this is the relation between small g and capital G. small g equals to capital G capital M by R square. Now we see differences. What are the main differences between small g and capital G? We see distinction. So coming to this small g, this is acceleration due to gravity, and capital G is small g is acceleration due to gravity. And capital G is called the acceleration, that is a universal gravitational constant. Universal gravitational constant. So now its G value is 9.8 meter per second square on the earth. Now G capital G is universal constant, that's value is 6.67 into 10 power minus 11 Newton meter square per kg square. Now third one is G changes place to place. Small g value changes place to place. For example, so if this is the equator and poles, so at equator we have g value and poles also. At poles we have the g value, but these two values are not equal. Now if we change the place on the earth, the g value slightly changes. So now that is g changes planet to planet, or if we on the earth it is 9.8 meter per second square, and on the moon its value is different. So that is acceleration due to gravity changes planet to planet position also. Now this is universal constant, so this value does not depend on any factor or any physical quantity. Now coming to the work energy principle, first what is work? So work, how we can define the work? Whenever a force acting on a body displaces the body in the direction of force. So a force is acting on this body in this direction. Now due to the force it is displaced a distance s. Now the work done is W equals to the product of the force into displacement. Force into displacement. So therefore F into S. So if the force and displacement are in the same direction, so now this is a scalar product, W equals to F dot S or Fs cos theta. So this is the object, the force acting in this direction, it is displaced in this direction. There is angle between them, force and displacement. So therefore W equals to Fs cos theta. Okay. So if theta equals to 90 degrees, what happened? Work done Fs cos 90. Cos 90 is 0. No work is done. Means, so for example, the person carrying weight and is moving on the surface. So this is the weight mg, and this is the displacement direction. What is the angle here? 90 degrees. So in this case, the work done is 0. Now coming to the energy, how we can define the energy? The energy, the capacity to do work. We can define this capacity to work is called energy. So it is measured in joule units. Now that energy appeared as many forms. So here we see potential energy and kinetic energy. What is meant by potential energy? The energy possessed by the body by virtue of its position. This is the reference axis. So here the object is there. Now it is at a distance of h from this. Its mass is m. So in this case, the potential energy of this object is mgh. So now kinetic energy. The kinetic energy of the body by virtue of its motion. So for example, the body, its mass is m and moving with velocity v. So by virtue of its motion, the body gets kinetic energy. Kinetic energy is equal to half mv square. Potential energy is equals to mgh. Now expression for kinetic energy. We want to derive the expression for kinetic energy. So for example, this is one object. So due to the force, it is accelerated and it is displaced, and this is initial velocity and this is the final velocity. So according to the work, W equals to F into X, simply Fs. Theta is 0 degrees. The force and displacement are in the same direction. Theta equals 0, cos 0, 1. Now A be the acceleration. When we apply the force, it is accelerated. So F equals to ma. So therefore, substitute this value here. W equals to mas. Now we use the by using this formula, v square equals to v square plus 2as. So here initial velocity, the object initially at rest. So this is 0. Now v square equals to 2as. A equals to v square by 2s. Substitute here. Therefore W equals to m into a value v square by 2s into this. S gets cancelled. So W equals to half mv square. So this is stored as kinetic energy in the. So the work done here, the W into W equals to F into S. The work done is equal to the kinetic energy of the body because the work done on the body sets in motion. So therefore, the kinetic energy is equal to half mv square. So now we see the work energy theorem. So this is one object, so its mass is m. Initially, it's a position at x1. We apply some force on this. Due to the force, it is displaced from x1 to x2. Okay. So now along x-axis, the position is changed from x1 to x2 because of this force. So initially we consider the small amount of work done. So that is f dot dr is nothing but f dr cos theta. Okay. Now this is small amount of work done. For total work done W equals to, we integrate this. That is f dot dr. So we can write the f dot integral of f dr cos theta. Now the object is moving from x1 to x2. So the velocity also increased from v1 to v2. So in this case, w equals to, we write the integral from x1 to x2. So now the change from x1 to x2, that is dx, say f dx. But according to Newton's second law, F equals to ma m into dv by dt. So we can write m into dv by dx and dx by dt. So just divide and multiply with dx. Then F equals to, we write mv dv by dx. In place of f, we write here. Therefore, w equals to the integral x1 to x2. So mv dv by dx. Already is the dx is there. Okay, dx get cancelled. Therefore, w equals to the integral x1 to x2 mv dv. Now the limits also changes. X1 is v1 and x2 v2. So therefore we can write w equals to integral of v1 to v2 mv dv. Therefore w equals to m into v square by 2. The limits v1 v2. Therefore half m v2 square minus v1 square. So therefore the work done is equals to half m v2 square minus half m v1 square. So consider this is k2 equals to final kinetic energy of m v2 square and k1 is initial kinetic energy of m v1 square. This is v2. Therefore work energy is written as k2 minus k1. So this is nothing but w equals to delta T. So delta K is change in the kinetic energy. So now this is the work energy principle, work energy theorem derivation. Okay. Now, next coming to the conservation of energy, we see the case freely falling body. Now, one object is freely falling body. Initially, that is at a point A. Now, it traveled a distance of x and reaches the point B, and then touches the reference level or ground. Okay, this is the case. It is the freely falling body. Freely falling body, initial velocity is zero. Okay. So now we consider 3 points: point A and point B and point C. We see the energies of this object when it is coming downward direction, or we calculate the total energy at point A, total energy at point B, and total energy at point C. Total energy in the sense, so when it is at point A, so it has kinetic energy as well as potential energy. How much these values? Now total energy E equals to sum of the kinetic energy plus potential energy. So now we calculate at point A. So initial velocity is zero. Now S equals to H. So kinetic energy is equals to half mv square. So this is zero. Now it is zero. Potential energy is equals to mgh. Now here this is the potential energy. Total energy is equals to E total equals to kinetic energy plus potential energy at A. So E total equals to, this is zero and this is mgh. Now the total energy at A is equals to mgh. Now at point B, so it traveled a distance x from A, and this is B, this is reference point. So total is distance is x. Now this is x, this is h minus x. So therefore, at point B it has some velocity v. Now here it traveled from A to B, s equals to x. So we use the formula v square minus u square equals to 2as. Initial velocity is 0. So v square equals to 2as. A is nothing but acceleration. It is coming downward direction. A equals to g. So that is 2gx. Okay. So therefore kinetic energy is equals to half mv square. So v square value substitute from this, that is half m 2gx. Half of gets cancelled. Kinetic energy is equals to mgx. Now potential energy is equals to mgh. In place of h equals to, so that is h minus x. We write here. So therefore the potential energy is equals to mgh minus x. Now E total energy at point B is equals to sum of the kinetic energy plus potential energy. Therefore, kinetic energy is half m only mgh plus mgh minus x potential energy. So mgx plus mgh minus mgx. So plus value minus value. So E total at point B is only mgh. Coming to the point C, at point C, now it touches the ground. So here h equals to 0. Okay. So now it has some velocity. The velocity is v. Now velocity of the is v. Therefore the kinetic energy is equal to half mv square. We use the formula v square minus u square equals to 2as. Okay. So it traveled a distance h. H equals to h. Initial velocity is 0. V square equals to 2. A is nothing but g. 2gh. Now therefore k equals to mg half mv square. Half mv square is nothing but 2gh. 2 gets cancelled. K equals to mgh. Now potential energy is 0. mgh. H is 0. Therefore 0. E at point C, the total energy, sum of the kinetic energy plus potential energy. So E total is equals to mgh. This is 0. So by observing 3 points, A, B, and C, now travel a distance h from A to C. So at 3 points, EA equals to EB equals to EC. So here MGH, MGH, and MGH. That is nothing but. So in the case of freely falling body, if you take at any point, the energy is constant and conserved. So, but the sum of the energy changes, but the total energy is constant and conserved. Means at some points the object has only kinetic energy, at some points the object has only potential energy. So during its motion, so it is some of them. So the total energy is remains constant. So that means the energy of the universe is constant and conserved. So we cannot create and we cannot destroy the energy. So but we can transfer the energy from uh, one point to another point, one form of the energy to another form of the energy. So the total energy of the universe is constant and conserved. So this is the conservation of energy principle. We cannot create and we cannot destroy. So we cannot We cannot create and we cannot destroy the energy. But we can transform the energy. We can transform the energy from one form to another form. For example, a river is going. So we arrange the turbines. So with the speed of rivers, the turbines will rotating. So the rotation is mechanical process. Due to this turbines rotation, so we convert this mechanical energy into electrical energy. So here the process involved here is mechanical energy. Due to this is converted into electrical energy. So this electrical energy is supplied to our houses. Now this electrical energy appeared as the light energy. If we on the switch, and this electrical energy can give to the heater, electrical heater. So that gives the heat energy. So that means we cannot create the energy and we cannot destroy the energy, but we can transform the energy from one form to another form. So this is conservation of energy. So the always the energy is equals to sum of the kinetic energy plus potential energy. So sometimes the kinetic energy is maximum, potential energy is minimum. Sometimes the potential energy is maximum and kinetic energy is minimum. And sometimes so it has only kinetic energy and sometimes it has only potential energy. So but the total energy E total is equals to constant and conserved. Linear momentum. The linear momentum is represented with P. So P equals to the product of the mass and velocity. So therefore P equals to m into v. The mass multiplied with its velocity is equals to momentum of the particle. So for example, this is one system. So the system consists of so many particles. Particle 1, particle 2, particle 3. Its mass is m1, its mass is m2, its mass is m3. So now the system is moving with velocity. Now its velocity is v1, its velocity is v2, its velocity is v3. Now therefore, so p equals to so m1 v1 plus m2 v2 plus m3 v3 and so on. So the total linear momentum of the system is p1 plus p2 plus p3 and so on up to pn. So this is the conservation. linear momentum. Or we can write coming to this here. So in next class we will see the remaining topic.